Hello, Year 11. Thanks for coming. Going to be doing a crash course today on periodicity. Going to be looking at the periodic table. Going to be looking at Group 1, Group 7. Oh, see if I can stop all that. Group 1, Group 7, Group 8, and transition metals. And hopefully by the end of the hour, you're going to have a slightly better understanding of how you can use the periodic table during your exams. Thanks to everyone for coming along. Got 7 people online already, which is cool. I hope you enjoyed my amazing chemistry jokes. I really struggle with those. So I pulled out some of my best ones there on the chat. Okay. So usual thing, what I'm going to be doing is giving you the hopefully less than 1 hour crash course, and then I'm going to run through your preliminary work that I gave you guys to do. And then you can do the follow-up work in order to hopefully solidify some of that. Okay, so I'm going to share my screen. Let's see if we can get our notes all up and running. Okay. So, usual thing. Now, in this case, I haven't actually gone through, I haven't pulled the bits out of the specification because they're kind of all over the place. So I'm just going to do the usual learning objectives. During this, I'm going to be looking at the trends and patterns in the periodic table that you guys are going to be able to use during your exams to hopefully make this a whole lot easier. We're going to be looking at atom size. I'm going to add a few more extras to this. So we're going to be looking at atom size. We're going to be looking at colors and trends in the colors of the groups. And we're also going to cover the other physical properties as well. And we're also going to look then at reactivity. If there are questions that you guys have, please ask them on the chat. I've got the chat window open, so I'll be able to answer those as we go through. So, okay, I'm also, I've put in an unusual practical part of this particular webinar, which is on the carbonate stability. Now, carbonates, I keep seeing carbonates appearing in questions on our Edexcel papers. And so I just wanted to give myself a reminder to cover them. I'm going to talk about the solubility of the carbonates and also the stability of them. There's a practical that has come up twice in the last 8 years that I just want to quickly mention and talk through. But I'm going to be focusing primarily on Group 1, Group 7, Group 8, and the transition metals. And I'm going to go through it in that order. That third learning objective is what I'm going to be focusing on. And each time I go through each of the groups, I will then link that back to the 3 learning objectives in the very first one, the atom size, colors, reactivity, and physical properties. Just before I move on from those, I'm just going to really quickly put out to the class the physical properties. And I seem to find that students really struggle with naming physical properties. And I think there's a small amount of confusion about what a physical property is. And I just want to quickly give you a few that you can always have in your mind when that word physical comes up in chemistry papers. So would anyone like, now I always say learning 3 is always a good shout for any one of these particular questions when I'm asked to quote them. Would anyone like to quote me a physical property of an element? So I'll put that out to the classroom first of all, and then I'll make some notes on them as they trickle in. So I'm looking for 3 physical properties and for you guys to be able to name. And then I'm going to drop into Group 1. See who's going to come up first. I ought to be collecting, of course, my I ought to be collecting the commendations for people giving me good answers. All quiet on the answer front. Lithium is soft. Okay, yes, Donna. So you've picked up one there. So this idea of softness, it's not really a great one to be saying. Could you just change that to a word if you were describing? I love the fact that you've given me the Group 1 metal as well, which is really nice. Lithium is actually the hardest of all the Group 1s, all the Group 1 metals. They get softer as we move down, and that'll appear when I'm doing the Group 1. So I'm actually going to pull that out and put strength. I'm going to put that in as number 3, strength. Any others? Well done. I like it. So we've got boiling point. That's a great one. Now, just to say, you can at that point say straight on the back of that melting point, that is a separate one to have. And if you really were stuck, I would always say to give those as two. Malleability, I like it. I love that. The question mark. Yes, malleability is a physical property. Now, it's not one that I'm going to put down, Lucas, but it is a physical property of something, whether or not it is malleable, and metals are malleable. The other one I'm going to give you is solubility. Solubility is a really nice one, whether or not something dissolves in water. So those, boiling point, melting point, solubility, strength. I wonder whether or not anyone can give me others. Another one which I won't put onto my list for you to learn, but is odor. Color is another one. That's a physical property. And conductivity is also another physical property. So I'll put conductivity there as well. I'll star that one, conductivity. And that might be one for me to talk through in terms of conductivity, in terms of trends in the table. Reactivity, like Dana, that's not a physical property. And that's something that I really need to set right in this webinar. A physical property has nothing to do with its chemical reactions. What about if it reacts with air? By the way, reacts with air / oxygen. That's a chemical property rather than a physical property. Physical properties are how something appears, how something tastes, how something feels, rather than how it behaves. And that's the thing that I really want to just pick up at that point. Okay, so let's have a look at group one. So now I've done something with the periodic table before I started the webinar, which was I just wanted to highlight certain people in the periodic table for you guys to know. And the ones in yellow are ones that come up time after time after time in chemistry, and they're elements that you really should be able to quote small details about, especially things like atomic masses. They're really useful. So hydrogen, pretty much all of group one, you'll notice that I stop at rubidium, I stop at potassium, and I don't go further down. The reason why is rubidium and cesium you never ever get to see because they're so reactive, they're too dangerous to do. And that's something that does come up in papers every now and again when they will say, explain why Stephen can't do the practical using rubidium or a practical using cesium. And the answer would always be, it would be too dangerous to do. It could potentially cause an explosion. Because if you're doing reactions with very reactive metals that really are running dangerously close to causing hazards, so we tend to avoid them. Okay, the first one I want to quickly point out to you is a trend in the periodic table. So I just want to really quickly when we start, let's just quickly make a few notes on the periodic table itself. Now, the periodic table has an order. It is designed in such a way for us to be able to build atoms from it. And there is a very particular order it is given in. And this question appears quite frequently on Excel. Would anyone like to tell me how the modern periodic table, the one that you can currently see on your screens, would anyone like to tell me how it is ordered? So looking at the table, and remember, the table tells you so you can get it. Atomic number. Yeah, Lucas, well done. Spot on, increasing. Donna, that's a key one that I need to point out. So, Donna, it is not by mass. It is by, Lucas is spot on, it's by increasing atomic number. Let's just have a quick look at that and highlight some of those numbers. And remember, the atomic number is the bottom one. So if I just make that a little bit smaller, so hydrogen is number 1, helium is number 2, lithium is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And you can see that there's a pattern here, which it is increasing by 1 every time. Now, Dana, you said mass number. And I now need to point out to you why that's not true. And this was thanks to a really famous chemist, the founder of the modern day periodic table, which is Arrhenius. Oh, blimey, I'm wondering how I spell that. Arrhenius. It's not Arrhenius, is it? Oh. Can anyone tell me who the modern periodic table is written by? The first name's Dmitri. And surname is Mendeleev. So the periodic table was created by Dmitri Mendeleev. I can't spell Dmitri. Mendeleev. And he's a very famous chemist. And the order is by atomic number. And it increases by 1 every time. And it is not by mass. Now, the reason why is because if you actually look at the periodic table, there are certain people who don't run in order in terms of mass. And the really famous one is tellurium and iodine. So if I quickly highlight these guys here, and you look at their numbers, they go from 52 to 53. So the atomic number is in order, but the atomic mass isn't. So the atomic mass has gone from 128 and has now dropped. Now, what Mendeleev did was he actually switched those two around because he wanted iodine to be in the group 7. So it is not by mass, and those two are a very famous pair of elements that actually remind you that it really isn't by mass, and it's by atomic number, which is the number of protons, of course. Okay, next thing in terms of the periodic table is, let's just quickly go back to it. It is also, of course, it allows you to build electron configurations. So you guys learn up to calcium in your electron configuration lessons. That's ridiculously oversized. Let's see if I can reduce that. Go down to there. So you stop at calcium, and calcium's electron configuration is 2. This is where it would be really useful if I could actually put like a, let's see if I can put a shape on top of these guys down here. And I wonder whether or not I can make that shape. I bet I can't. No, I don't think I'm good enough to do that on this particular one. I want a fill shape. Basic shapes. It won't let me fill it. Ink to shape. Ink to shape. I don't know quite. Maybe let's try that. And then if I see if I'll go ink to shape. No, it really doesn't want to let me do that. That's frustrating. So for calcium's configuration, it is, and I'll draw a little arrow going up, it is 2, 8, 8, 2. How did people actually work out the atomic number? God, that's a really, really, really complicated question. The answer is they didn't know about the atomic number until way after the periodic table had been created by Mendeleev. The atomic number was deciphered after they discovered the proton in 1912-ish. And they then, of course, they then did physics practicals where you can remove electrons from people electrically. You strip them, and the number of electrons balanced the number of positive charges that was left over at the end. It's a good question. So what I want to show you is how you can use the periodic table to decipher those numbers. Oh, ink to shape. I've just seen what that's just done. That's quite clever. So I just want to show you how that can be done. So let's choose another element, and I'm going to show you where these numbers come from. So let's just choose, just for fun, let's choose, need to choose a color as well. Let's choose phosphorus. So phosphorus is element number 15, and its configuration is, if I read the table from top down, left to right, In the first row of the periodic table, there are 2 elements, hydrogen and helium. If I look at the next row, there is also then 8 elements in that period. And then if I move across, 1, 2, 3, 4, 5 to phosphorus. And there is its electronic configuration. So phosphorus is 2, 8, 5. And the periodic table is designed to allow you to do this. And it's really important that you've been shown that and you get to grips with it, because you're going to need that when you take A-level chemistry, because the periodic table goes far further than what you guys are realizing yet. And that is going to be really, really handy. So I can do another one. Let's do neon, which would be 2 in the first row and then across to 8 for neon. So 2, 8 for neon. If we did oxygen, it would be 2, 6 because of 1, 2, 3, 4, 5, 6. So oxygen is 2, 6. And it's really nice to see how the periodic table is allowing you to do this. It is built to be able to give us a helping hand in chemistry. So it's something to bear in mind. And if you've got any further questions on that, please give me a shout and I'll happily take you through it and do some practice with you guys. So we've got a couple of things just straight away from the periodic table. You can work out electron or electronic configurations. And all you're doing, electronic configurations, and you're doing this by reading across the rows. So calcium being 20, when you read across the periodic table, and if I just quickly sketch one, yeah, and we go, calcium is here, and I go, no, it's not, calcium's next door to that one, so calcium is next door, calcium is here, and I go 2, and then I read down across the next line, and there are 8 in that line, and then 8 in that line, and then it ends at 2 at calcium. So 2, 8, 8, 2. It's just nice to see how it works and to be able to use that. It means that you don't have to remember numbers or you don't have to be counting things. You just read it off the periodic table. I'm actually gonna leave those there for the notes. Okay, so it's just nice just to quickly give you some ideas of what the table's doing. The next thing, do you know what? Before I move on to that, I'm just quickly going to talk about groups and periods. So a group is a column in the periodic table. They go down. So this is the groups. And let's take group 1 as the example. So we've got lithium, sodium, potassium, and then we've got, not having a good day today. And then cesium and then francium. And this group, as you go down the group, the atoms increase in size. Now, this is a general trend in the periodic table. So, fact about groups, atom atomic radius increases down a group. And if people are wondering, down group, if people are wondering how you measure the size of an atom, what you actually do is you measure from the nucleus, should try and keep that a little bit better actually, from the nucleus to its outermost electrons. So if I was to look at lithium, for example, with only 3 electrons and 2 shells, the size of lithium is from the nucleus to that guy. If I look at sodium, sodium is going to be larger because it now picks up the additional shell on the outside. So they increase in size, and of course potassium then being the largest of those 3. And it's nice, I've then just grabbed those just to show you where the size comes from in terms of the configuration. So we've got lithium, first shell holding 2, second shell with 1, and then the atoms are increasing in size as we move down the group. So I'm going to come back to group 1 momentarily, but now that I've just covered groups, and also to mention that groups are special, because I often like to say that the word groups in chemistry, especially in terms of the periodic table, simply means family, because these guys are in groups, have similar chemical properties. Similar chemical, and that's a key thing. Notice that I am not saying that this is a physical property. I'm now going into chemical properties. So this is how This is how they're going to behave. And the reason why they do this is because they have the same number of electrons in their outer shell. So, and by the way, I shouldn't say that. That's not a good word now in chemistry, especially at GCSE. I'm just going to put in brackets energy level. I always do that now. That is what has to be done in your exam. I like the outer shell concept. I like the shell concept, but we do now need to be using the words energy level in our GCSE answers. So we have a trend in the atoms in atomic radius, in terms of their size, and we've also now got a property of reactivity. We're saying that they're all similar, but there's going to be a trend here as well. And that is, now this is where the groups now divide off, because we know that metals lose electrons and non-metals gain them. So we then need to look at those chemical properties a little bit more carefully in terms of the behavior, and I'll do that when I switch to group 1. But just whilst I'm here, I'm now just going to quickly drop into the periods. So the periods in chemistry are the rows. So in the periodic table, if we look at a period, we're looking at a row. So now I've overdone. Do you know what? If I'm going to do that, I really ought to do the number of boxes correctly. If I look at, let's look at period 2, for example. Now, period 2, I shouldn't really choose because it's, of course, a split group because the transition metals are there, but it's a 2 and a 6. So as we go across, so this is period 2. So this is lithium, followed by beryllium, followed by boron, followed by carbon, nitrogen, oxygen, fluorine, and neon. So as they move across now, people often ask me, do we ever need to know anything about the periods? And at GCSE, the answer is no. But at A level, you do pick up, people go, are there any trends in it? And I'm like, there is. And the trend is that the atoms actually get smaller as you move across. The reason being is that they have the same number of shells, but more protons. What that means is you're going to suck in those electrons more as the positive charge in the center in the nucleus increases. So the atom size now decreases across a period. Now, you don't need to know that for GCSE, but it's a lovely thing for me to add. All you actually need to know is that the periods go across. People often at this stage ask, how can they put that in a question? So what they will do is the question there would simply be name the element in group 1, period 3. So what they're doing is they're testing your understanding of what these words mean. So you're just going to drop straight into your periodic table and you'll go, right, I need group 1. So I've got column number 1 and I've got period number 3. 1, 2, 1. Easy to make that mistake. Everyone misses the top row, by the way, because hydrogen's often set off to one side. So the answer would be sodium in this case. So that's all they're doing. They're testing that you know what they mean. And it's like a grid system for the periodic table and to be able to isolate particular elements. But that's all you need to know at GCSE. Okay, so at this point, I want to drop in now to group 1. So we love group 1. It's what students always remember in chemistry. There aren't a huge number of demos which people walk away with going, oh, I remember seeing that one. You know, when time goes by, you forget things. But you see group 1 so heavily throughout your chemistry careers at school that it tends to stick. And also because everybody wants to see the bangs, so to speak, as we go down the group. So group 1, and I'm now going to list them. So we've got lithium, we've got sodium, we've got potassium, we've got cesium, and we've got francium. And as we go down, we can apply our new trends. So we've got the atom size is increasing as the shell number increases. And now we drop into, so we've got atomic radius, atomic rad increases down group. We know this, got that already. But now we pick up their chemical properties. So how they're behaving. So we know that, and if now I'm going to go into a slightly more detailed diagram. Lithium has 3 protons in its core, and it has 2 shells. And we know that metals must and only ever give away electrons. They lose electrons. So lithium needs to lose it. And in order to do this, it has to break the attraction that it has to the nucleus. And that's the key thing here. It's about, I've got to actually break a bond. And what that means is it also reminds me that the process is going to be, in this case, the removal of that electron will be endothermic because I'm going to break a bond, mexobendo. But that attraction is very big because it's very close. As we go down the periodic table, the atoms get bigger. So in sodium's case, we've got 11 protons in the core. But now we've got an additional shell. And people often say, does the charge in the nucleus not, does it not counteract the distance that the electrons are from the nucleus? And the answer is no. The reason being is we've got electrons underneath pushing that electron away. And even with the additional protons, that shielding from the nucleus by the electrons underneath, so I've got 2 electrons there and 8 electrons. These electrons are going to shield them against that attraction. So this is now going to be much easier to lose. So we pick up a trend. And the trend is as you go down the group, reactivity increases. And they're going to, of course, ask you to explain this. And you're going to bullet point your answers and say the outermost electrons are further from the nucleus, This means there is a weaker attraction to the nucleus, therefore it is more easily lost. So that question comes up a lot and students tend to waffle a great deal on that particular question, and I really, really don't want you to. So, okay, so the next thing about group 1, we need to pick up some nice facts about group 1 as well. So the next trend, we pick up trend number 2. So that's trend in reactivity. Let's go trend in reactivity. So we pick up the second trend. So the second trend, trend number 2, so to speak. So trend number 2 is it is how soft they are. I'm going to put hardness. You don't tend to say softness. You tend to do it in relations to how hard they are. And there is a pattern here because we now have to talk about metallic bonding. So if I have lithium, and lithium looks like this as a metal in its bonding, all the atoms lose their electrons, and the electrons are in a delocalized C and are able to move through the structure. This is why they can conduct electricity. So the structure, it's nice for me to drop into a bit of bonding. So metallic bonding, the key thing to remember are that we have got a giant lattice of cations, surrounded by a sea of delocalized electrons. And of course, these electrons are able to move through the structure and hence conduct electricity. This is called metallic bonding. And if you've got cations and you've got negative electrons, you're going to have an electrostatic force between them. So you're going to have a strong electrostatic attraction between cations and the deloc electrons. And this makes them strong. Now, in terms of the trend in hardness, look what happens in terms of the change in the diagram. So I have got 4 electrons. Let's highlight my electrons. I've got 4 electrons and 4 cations. And this is lithium. Let's now look at what the diagram looks like for sodium. The cations are larger. Now, what that means is that they are still +1. However, we have now got the same 4 electrons in the C. However, they're having to hold together much larger atoms. What that means is you now have a weaker attraction between the cations and the delocalized electrons. What that means is as you go down the group, so as you go, here's the trend, as you go down group one, their hardness decreases because the bonding weakens. People often say, I don't understand why having larger cations would make the bonding weaker. The analogy I often talk about is the idea of holding on to a tennis ball and a beach ball. If I give you a tennis ball to hold on to, I know it's a terrible diagram of a hand. If I give you a tennis ball to hold on to, then you will put both hands top and bottom, and you'll be able to apply all of that force over the very small tennis ball, and it would be very difficult for me to rip that off. And that's because the bonds that the tennis ball have, the forces involved are much greater because it's smaller, it's more compact. So the forces are being distributed over a much smaller area. If I give you a big beach ball to hold on to, I know the hands are creepy, aren't they? If I give you a beach ball to hold on to, when you try to apply that force, you're having to distribute that force over a much larger atom. And what that means is that your forces is going to be decreased. So it becomes much easier to be able to break that off. Hence why the melting point and strength decreases. So hardness decreases, down group one, hardness decreases. This now links, of course, immediately into melting point. So trend number 3, if you wish, would be melting point. So, and the great thing is you don't really need to remember this because the trend follows hardness. So as you go down group 1, the melting point, the MPT, will decrease. So the reason being is the forces, hardness decreases. The hardness decreases because the forces holding them together decrease. So it's just nice to see these trends all appearing. So we've covered 2 physical properties, both hardness, strength, and melting point. We've also then covered reactivity in the trend and atomic radius. You've picked up 4 there. So let's go back to my learning objectives. So we've got atom size, reactivity, and I've just covered melting point and strength. Now, just to mention conductivity, people often say, well, how would the conductivity vary? Well, the conductivity will be almost the same. There will actually be a slight, no, it actually goes on the softness link. So the conductivity of the softer ones is slightly higher than the harder ones because the harder ones like lithium are more compact, meaning the electrons have a tougher time to be able to move through it, so the resistance is higher. But it's nice that we've walked all the way through this. I am just going to mention color, of course, and you don't really need to for the group 1s because the answer is they're all metal and they're all silver. So no trend tends to appear for that one. Okay, the next group I'm going to drop into at this point. Do you know what? Let's go across the periodic table from left to right. Let's now have a look at the transition metals. So now the transition metals you don't need to know an awful lot about. So let's go transition metals. And this again comes down to facts. And we're looking for trends, of course. Transition metals. Now, okay, first thing is there are patterns in the transition metals, but it becomes a little bit complicated. And you actually don't need many of them. You just need to have the rules and you just need to have the actual physical things that they do. So the first fact that we're going to pick up is they form, and that's a key word, form colored compounds. This is unusual. If I take, so an example, e.g., if I take sodium, which is not transition metal, and I react it with oxygen gas, I will make sodium oxide. And I now balance the equation. And sodium oxide is the compound, and it is white. It is white because it is a group 1 metal. It is not transition. But however, if I take silver shiny iron, and I take iron and I react it with oxygen, then I'm going to form iron oxide. Now that I've actually formed iron 3 oxide here. It's really important for the Roman numeral for the transition metals. That'll come for fact number 2. But now I'm going to balance it again, of course. I'm going to do a 2 there to get a 4 there and a 3 there. And the important thing about this is that is brown. I shouldn't do it in red. It's bad for me to not use the correct colors when I can use the correct colors. More colors, let's go for brown. So this is brown in color. So we pick up, this is a brown solid. So transition metals all form colors. I'm tempted to give you one more, but I'm tempted to. If I do another example of one that you might need, let's think of a good one. A good one for colors with an oxide. Can't think of one off the top. I really ought to as well. Copper oxide. This is copper 2 oxide. And copper 2 oxide is one that you also need to know the color of, and that is black. Now, it is black. That is colored, because if it wasn't black, if it wasn't colored, it would be white. And this is black. Another compound of copper is copper carbonate, copper 2 carbonate, and that, of course, is turquoise. That's blue-green for your exam. So lots of nice colors there. I'll come back to that of stability for carbonates as well. Okay, so the next fact for the transition metals. Let's do, I'm trying to find the space for this. Okay, next fact for the transition metals. Fact number 2. They all have high melting points, high MPT and BPT, except with one exception. Melting points and boiling points. Exception to this rule is mercury. So mercury is a liquid at room temperature. It's the only one that stands out. All the rest have got very high melting points. They all form +2 cations in their lattice, and they all have 2 electrons in their outer shell. That's a key thing. Fact number 3. Fact 3. All transition metals, all TMs have 2 electrons in their outer shell, There are exceptions to that rule. However, you don't need to know them for GCSE. They all have 2 electrons in their outer shell. That's why you stop at calcium, just so you know, on your electron configurations. 2882. You stop there, you don't go any further. Okay. Next facts for the transition metals. Let's have a quick look. So key things just to pick up. I now just want to mention magnetism just for 1 minute. This is a horrible word in chemistry, and I actually tell everyone to flat out delete it. There are 3 metals that are magnetic, and only 3. And those 3 are right next to each other in the periodic table. So the magnetic folk are iron, cobalt, and nickel. They are the only ones that are magnetic. All the rest are not. So this is not a common property. Key thing to pick up. Okay, the next thing is the ions that they form. So fact number 4, fact 4 is they form many oxidation states. Now I'm giving you a very posh word there from chemistry. Oxidation states just simply means charges. So for example, you can have this compound. That there is iron 2 oxide. And the reason why it's iron 2 is because it is made from O2 minus and it is made of iron 2 plus. So the 2 here is the charge on the transition metal ion. Okay, we've got iron 2 plus, but we also have, as we've seen earlier from our brown iron 3 plus. So we actually have 2 common oxidation states, common charges for iron. And that's the iron 2 is green and the iron 3 is brown. It's always nice to have our colors appear, which you do need to know, by the way, for your chemical tests. So lots of these do them. Vanadium does loads. Vanadium does 4 different charges: V5 plus, V4 plus, V3 plus, and V2 plus. And it stops there. And each of these oxides each of these charges have different colors. So vanadium 5 plus is yellow, and then V4 plus is blue, and then V3 plus is green, and V2 plus is violet, which is kind of cool. So each of these charges, they form these multiple charges and therefore multiple different colors as well. So the transition metals are a nice, easy set of metals, but in terms of trends, there aren't really many. Okay, next group that we're going to switch over to is we're going to switch over to group 7. Now, group 7, this is the halogen family. Now, the halogens really need a lesson all onto themselves. The halogens, group 7. And group 7, halogens, halogens, group 7. And this family are the nastiest bunch of people. These are horrible, horrible elements. But they do have, but they are incredibly important. They appear all over the place in chemistry. So we have fluorine. Please remember that fluorine has a symbol of F, not Fl. Chlorine, bromine, and iodine. So we've got, now people often go, what about astatine? We ignore astatine because astatine actually holds a world record as being it is the rarest element on the entire planet. There is 2 grams of that element in the entire world, and that is distributed over the planet. You can find tiny traces of this in nanograms in certain rocks, but we've never had enough of it to be able to actually test it. But group 7 is so important because, oh, my laptop has just come up saying the battery is going to die. Let me just quickly plug it in. Sorry, folks. There we go. Everyone's awfully quiet today. So, once again, the same trend appears in terms of atoms-wise. I've got fluorine, I've got chlorine, I've got bromine, I've got iodine, and I've got astatine. Their atomic radiuses are increases. This is because it follows the general trend we saw in groups earlier. The group, remember, means family. These are all related. So their atom size is increasing. The next thing to talk about is so let's put that fact. So atomic radius, atomic rad increases down group. Increases down group. I'm just going to put GP. Okay, then we need to talk about their reactivity. So in terms of reactivity, as we go down the group, they do the exact opposite of group 1. In group 1, the most reactive one is at the bottom and the least reactive is at the top. This is because they're trying to lose electrons. Their electrons are needing to be lost, which means the further away they are from the nucleus, the more easily they're lost, so the more reactive they become. However, with group 7, they're doing the exact opposite. What the elements are doing, and I'll take chlorine as the example. Chlorine is element number 17. 2 electrons in its first shell, 8 electrons in its second shell. Notice how I paired them up, it's easier for counting. And 7 electrons in its outer. So what this now is trying to do is they are desperate to gain 1 more electron to fill that outer energy level, to become the noble gas configuration. So they're doing the exact opposite of the group 1 metals. The group 1 metals, let's have a look at sodium, element number 11, which is 2, 8, and then with 1. They're trying to lose electrons, whereas group 7 are trying to gain. So what that means is that as you go down the group and you notice what they're doing, which one is going to be able to attract that negative electron more? Well, the answer to that is fluorine. The reason being is electrons are negative. The part of the atom that's going to attract those negative electrons is the core, is the positive protons at the center. And the smaller you are, the easier it is for that electron to get closer to the nucleus. So the reactivity does the exact opposite of group 1. It decreases down the group. That's really unusual. It's just a complete polar opposite because we've switched from one side of the table to the other side of the table. And it's nice that to be able to realize that the periodic table and how it's distributed tells you what those people are going to be doing. So, okay, we've now done reactivity. The next one, and we've also explained it. If they asked us to explain this, we would say atoms increase in size increase size down group, outermost electrons, outer shell further from nucleus. Notice the similarity. Outer shell further from nucleus, harder nucleus, harder, less attraction. Oh. Well, hello, I'm back. Sorry about that, folks. My laptop died. It came up saying your battery is low, and then I plugged it in and I forgot to turn it on at the switch. Oops. Okay, back to it. Let's see if we can finish this off. That's really funny. Try again. Make sure to leave a comment. Like? I don't get it. Okay, let's go back to my notes. I hope it's kept all my notes. It should do. Right, back to this. Look at that, right where we left off. Okay, so the outermost outer shell, outer energy level is further from nucleus. I'll put from. I like from nucleus. Less attraction. I don't like saying I'll put electron. Less attracted. Harder to gain. You're done. So that explains how their reactivity changes. Now the next one, if we get to 40,000 likes, we do another video. Okay, so the next one is for group 7 is very special, and that's color. So fluorine, it's a nasty gas. In fact, fluorine is an element to know. Honest to God, guys, learn about this lady. This lady is insane. She is the most reactive element in the known universe. She can set fire to diamonds in the dark. Fluorine is crazy reactive. And that way, if you know about her and that she is number one, fluorine is the most reactive element. That means you get the trend down the group as well, which is really nice. And fluorine is a pale yellow gas. In fact, it's so pale yellow you can't see it. It's usually called colorless. They will actually allow you to call that a colorless gas. You then pick up chlorine. Okay, so chlorine is another nasty element, and she's a green gas. Now, by the way, she is a green gas. However, SL, because it's very rare to see quantities of chlorine high enough to see her green color, what that means is we tend to describe her as a yellow gas. And both of those, yellow/green gas. Next, now you notice the colors are getting darker. There's a pattern here. The next one is bromine. Now, bromine is my least favorite element. Bromine is terrifying. And I'm trying desperately to make my color palette work here. And bromine is a brown, I like the artistic flair here. It is a brown liquid. And it also gives off brown gas. But bromine itself is a brown liquid. Br2 is liquid and it is brown. Chlorine, of course, is Cl2, traveling around in pairs, as we all know. Chlorine, let's find black, there we go. Chlorine in pairs, fluorine is a pair. So what's happening here is they're getting darker down the group, and you see the state change. This gives us the melting point and how it's increasing. So we've got to talk about that as well. The next one is we pick up solid gray, silvery gray iodine. Iodine is a solid, I2 solid, and it's described as a gray solid. Now, iodine is very special because it has these rather bizarre colors associated, because we saw bromine being brown, 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 but iodine is a very odd thing because it starts off this grayish, silvery, dark gray color, but it gives off dark purple vapor. Iodine as a gas is dark purple, and when iodine is in water, it's brown. We're going to talk about them in water as well. Fluorine in water, a solution of fluorine water. You can't actually get it, by the way, because it reacts with water. That doesn't happen. It's impossible. She's so reactive, she sets fire to water. Not fire, actually, but it does react with it spontaneously. If you put chlorine into water, if you get chlorine water, it's a pale yellow chlorine water. And then if you put bromine into water, it is orange. That's important for the test for the alkenes. Orange bromine water turns colorless. And if you put iodine into water, it is dark brown. So in every scenario, they're getting darker as you go down the group. And that's important. You've got to bear that in mind, folks. It's nice for me at this point also to mention some precipitate tests. Silver chloride is a white precipitate. This is the test for the chloride ion. Silver nitric acid followed by silver nitrate, and you form white silver chloride. And that's a white PPT. And then we get silver bromide, and silver bromide is darker. There's a pattern here that rolls over, and that's a cream PPT, precipitate. And silver iodide as a solid is a yellow PPT. They're getting darker as well. It's so nice to see the trends in our groups shining through in loads of patterns. It makes everything so much easier. Okay, how do you not get acid burns when we go to the pool, even though there's chlorine in it and water? Because it's not concentrated. They put very little in, but lots of water. So is it slightly acidic? Yes, it is, Lucas. That's why your eyes sting when you open them. It's not because the kids have weed in the pool. It is because when we add chlorine to water to sterilize it, not to clean it, because you add chlorine to water and you form HCl, which is hydrochloric acid, because it's in water, hydrochloric acid, and you also make HClO. That's called hydrogen chlorate 1, and that's bleach. That's mild bleach. And that is what kills bacteria. This one here kills bacteria. Yeah, so your eyes sting because of the hydrochloric acid, and the HClO kills the bacteria. And chlorine is toxic, and yet we still add it. And the reason being is we add it in such small quantities that it's safe. It's not going to affect us. We're a big organism compared to bacteria, which are tiny, weeny, tiny organisms. So it'll kill bacteria easily, but it won't kill us. Okay, so we've done reactivity, we've done atomic radius, and now we've done another physical property of color. Isn't that nice to see another physical property appearing? Atomic, color, reactivity, and boiling point. Right. I now need to, God, so important to have those learning objectives there to help me remember which ones I'm doing. The next one is to talk about boiling point. Free skin bleach. No, not enough bleach no, the bleach isn't in concentrations high enough to bleach your skin, Lucas. So fluorine is a tiny diatomic molecule. What that means is between fluorine molecules, the WIMPs are very weak intermolecular forces. If you look at now chlorine is bigger. The bigger the molecule, the stronger the WIMPs. So we have WIMPs here, but now a bigger molecule means stronger WIMPs. Stronger, weak intermolecular forces. Let's look at bromine. Bromine is massive. That's now become a liquid at room temperature. Yeah, this is now into covalent bonding and weak intermolecular forces. Bigger molecule, therefore stronger WIMPs, therefore higher melting point. And then you get iodine. Iodine is enormous. And her WIMPs are strong enough to make her a solid at room temperature. Kind of nice to drop into a little bit. Average is pH 6. Yeah, sounds about right. Cool. So we've done all of group 7 now, which is ACE. So we get tick off group 7. Tick, and TMs are done. Last one, group 8, otherwise known as the noble gases. Everyone loves the noble gases. Noble gases. Otherwise known as group 8. Okay, so the noble gases are helium, neon, argon, krypton, krypton and xenon. So these are our noble gases. And of course, the great thing with these is the trends are very straightforward. Number 1, yeah, reactivity. Reactivity, no. We don't need to talk about it because they are all unreactive. They have full outer energy levels, all unreactive, and I prefer the word inert. Yeah, they're all inert. I'm going to ask you to explain this. They have full outer energy levels. Outer energy levels. So they can't lose or gain. So won't lose or gain electrons. Cool out. Okay, next one, melt boiling point. They are all gases at room temperature. So this is boiling point. And of course, the great thing is, look at the atoms. They're getting larger. So Superman kryptonite. Yeah, sure. Would you say energy levels? I'd say shells first of all, Johan, and then I'd of course then put energy levels as in brackets. That's what I always do. I put both. Valences. Yeah, valence shell is the outermost electron, outermost energy level. So you can put either. Okay, guys, the atoms, we've got the same trend that applies to all groups. The atoms are increasing in size. Guess what happens to their boiling points? Well, even though they're atoms, they're still held together by WIMPs. What that means is, as they get larger, the WIMPs get stronger. So they're melting points. So bigger atom, stronger WIMPs, stronger, weak, intermolecular forces, higher boiling point, higher BPT. And that's it. Really nice that. Just to mention the noble gases really quickly, because every now and again a question appears which people don't like, and that is that xenon I think actually 1998 or 2002, it's either one of those dates. Xenon, being the biggest of the noble gases, they reacted it with fluorine, the Tyrannosaurus Rex of the periodic table, the most reactive substance in the known universe. And amazingly, they formed xenon tetrafluoride. It can be done, but I just want to mention, and the question that followed, number one, they asked you to balance the equation. They said, they gave you that formula and said, write an equation for the reaction of xenon with fluorine gas to produce xenon tetrafluoride. You put xenon in as a single atom, you put fluorine in as diatomic, and you put xenon tetrafluoride, and then you balance it as such. The next question that they asked, so the first one was write an equation. The next question that they asked was explain why chemists found this unusual. And the answer, of course, is number one, bullet point number one, xenon is a noble gas. Second bullet point, it had a full outer energy level. It should not form compounds. You're done. It shouldn't react with fluorine. So it has been done, and those reactions are possible under very, very, very strict circumstances and with crazy people like fluorine. But I just wanted to quickly mention it. It was a clever way round of getting you to explain why it's noble by showing you that it was in a reaction, which freaked out an awful lot of people. Right, that brings me to the end of my webinar on, because I've now covered all of my groups plus size, identity, and all that jazz. So I'm just going to quickly now have a look at the preliminary work. So first one, they looked at the amount of gases in the atmosphere, and nitrogen, of course, is 78%. It's nice to know your percentages. Oh, I haven't mentioned carbonates. Nearly forgot. Okay, so just quickly to drop into carbonates. Okay, so first thing to mention to you is the carbonates that you guys should read. Oh, okay, hang on a second. And I didn't get what the Marx scheme says about energy. How did they get fluorine alone? Like just F2, if it is so reactive at Mr. Duncan. Johan, it's a really good question. Do you know what? Why don't you look it up? Look up the fluorine martyrs. There were 11 scientists that were were given the task to be able to extract fluorine gas. And I think 9 of the 11 died. So the answer is it's a very, very difficult thing to do. Fluorine gas is extracted via electrolysis of HF, hydrofluoric acid, which is one of the most dangerous acids in the world. I'm dropping into history now. But when you react it, we store it in PTFE, in polytetrafluoroethene. It's the only thing that can hold fluorine because it's already covered in fluorine. By the way, since I've just mentioned that, it's just going to drop into a bit of polymer chemistry. Yeah, this polymer here is called polytetrafluoroethene. Poly, tetra is 4 in chemistry, fluoroethene. Yeah, and that there is PTFE, otherwise known as Teflon in the shops. This is non-stick pans. This plastic is the most unreactive plastic that we have ever created, and it is the only thing that can hold fluorine. So if we had a canister that we wanted to fill with fluorine gas, we take that canister and we line the whole thing in PTFE. And so this is all PTFE, all the way around. And then we store the fluorine gas inside that. And even that will still eat its way out. Can only store it for about 9 months. Nasty, nasty stuff. And as I said, it's a really sad story. Like, I think out of the 11 scientists, as I said, I think 9 died. And one of the ones that survived lost his tongue and his eyes. It was a difficult task. And there were some really bad accidents. Okay, so onto the carbonates. Just quickly to mention that we've got sodium carbonate, we've got potassium carbonate, we've got lithium carbonate, and we've also got copper carbonate. These are the ones that you commonly come across. Now, I've suddenly realized I should have put those in order. I could have moved them around, actually. Lithium carbonate, I'm decreasing down, I'm moving down group 1, potassium carbonate, and copper carbonate. Right, so what I want to now talk about here is what's called the stability of carbonates. Now you guys need to, I'm going to take the solid of all of these. By the way, all of these, every single one of them is insoluble. The lot. None of these is soluble. So I take these solids and I heat them. If you heat carbonates, if I take solid lithium carbonate, solid sodium carbonate, potassium carbonate, and copper carbonate, and I heat them. So I'm going to heat these. Now what happens is that they will break apart. The first one that breaks apart is copper. This goes really easily. It forms black, starts off blue-green, and it turns into a black solid, turns black of copper oxide, turns black, that's copper oxide, and it releases into the atmosphere carbon dioxide. So it breaks apart. Now, copper carbonate does this really easily. And the reason why is because the copper is not very reactive. Copper is a low reactive metal, so it breaks down very easily. What that means is lithium carbonate will also break down and release CO2. However, sodium carbonate and potassium carbonate won't. This is because their reactive group 1 metals will hold on to that carbonate far more strongly. There's actually a far more complicated reason to that, which you learn at A level, but you don't need it. All you need to know is that lithium carbonate can break down, but the rest of the group 1s don't. They won't break down on heating. They're more stable because they have a more reactive metal holding on to it. Copper goes really easily. Okay, so at this point, I'm now going to jump straight into I'm just going to quickly check the chat. Oh, what colors solid fluorine if it exists? It'll be pale yellow, definitely. Okay, let's drop into my preliminary work. So nitrogen, 78%, nice and easy. What is the approximate percentage of oxygen in the air? Just, guys, I ought to do a webinar just on oxygen. You guys need to know, in terms of oxygen, you need to know, the practicals that show the 21% in the air. There's practicals that show that. The rusting one, ugh, it's horrible. The candle one, ugh. We also need to know the combustion of oxygen. We also need to know that it's diatomic and that it has a double bond between them. So in here we've got 2 crosses in there. Oh my goodness me, that wasn't very good, was it? So in here we've got 2 crosses, and I'll do it as super tiny cross dot. Yeah, there we go. And then cross and cross and cross and cross. I can't not do it now. So there's oxygen as a molecule, double bonded. And there's 21% oxygen in the atmosphere. Next one. One of the gases in the air is argon. It is called a noble gas because it is unreactive or inert. The percentage of water vapor in the air varies with weather. Rainwater is naturally slightly acidic because carbon dioxide dissolves in it. Carbonic acid. I like the fact that they've given you equation in words. Acid rain is more acidic because pollutant gases dissolve in the water. Identify the acid formed when sulfur dioxide reacts with water. This is sulfurous acid, not sulfuric. Be very careful. Acid rain is not sulfuric acid. If it was, we'd all be doing like the way that the witch does in The Wizard of Oz, which is if it rained, we'd all be melting. So it's sulfurous acid, far less acidic than sulfuric. Identify another pollutant gas that forms acid rain, and that's nitrogen dioxide. Try to stay clear of nitrogen monoxide. Just stick with the dioxide. SO2 and NO2 are all our acidic acid rain gases. Stage 2 problems caused by acid rain makes lakes acidic. By the way, guys, the yellow that I highlighted in this question is because I didn't do this. I realized that when I was writing it, I was like, problems. Well, me saying that the lake is acidic is not really strictly an issue. The issue is that it harms aquatic life. So I added that in, and when I went to the mark scheme, I highlighted because I was like, I'm really glad I did that because otherwise I would have not got that mark. That's what the mark is for. It makes lakes acidic and harms aquatic life. And it damages limestone statues and buildings due to the reactions with calcium carbonate. Next. Right, it then says bromine, chlorine, iodine, group 7. Tick the boxes that show the correct statements. The elements can be obtained by electrolysis from molten metal halides. That is correct. That's how we obtain them. We melt the salts and we electrolyze them. The elements with paler colors are lower in the group. Well, that's not true. We did that today. Iodine is black, is gray at the bottom. Bromine is brown at the bottom, so they're getting darker. The boiling points decrease down the group. That's not true either. They increase down the group, hence why iodine is a solid, but fluorine is a gas. The elements form covalent compounds with nonmetals. That is true, such as HCl, HF, HI. The molecules contain 2 atoms. They are diatomic. That is correct. And all are gases at room temperature. That is incorrect. Bromine is a liquid and iodine is a solid. Write a chemical equation to show the formation of the salt potassium iodide from the metal and the halogen. K plus I2 goes to Ki and balance. State symbols. Hydrogen chloride is a gas. HCl is a gas. Is hydrogen chloride, but in water, hydrochloric acid, so it becomes aqueous. Give the observations. So it says hydrogen chloride is dissolved in methyl benzene. When a piece of magnesium is added to the solution, there is no reaction. When the water is added to the mixture and shaken, a reaction occurs. Explain why. Right, hydrogen chloride so that's an acid. We know that HCl is hydrochloric acid, but remember, an acid cannot be an acid if it is not in water. So if it's in methyl benzene, which is just another solvent, it's not water, so it can't be an acid. So it goes into methyl benzene and it won't react. You'll see no reaction. But if they add water, then the HCl will move into the water. It'll turn into an acid and then react with the magnesium ribbon, hence the shaking. And it says, state and explain the observations. So when the magnesium goes in, the magnesium will react to form a hydrogen gas, which are the bubbles that we will see. The hydrogen chloride does not dissociate in methyl benzene. When water is added and shaken, hydrogen chloride moves into the water, dissociates, forming H+, reacts with magnesium to form hydrogen gas, which is what the bubbles are. Next, explain which test gives the results that cannot be used to compare reactivities. Test number 2, chlorine won't react with sodium chloride. That's really easy. Chlorine won't react with chlorides. They are the same thing. Yeah, chlorine will not react with chloride. That just will not happen. So it's a pointless test. So it won't help us in terms of reactivity. Which observation shows the displacement reaction occurred in test number 1? Displacement reaction occurs to the bromine, the halogen solution added is bromine. We're going to start off orange with bromine water. We're going to add sodium iodide, and it's going to turn dark brown because we saw earlier that the halogens, that bromine is orange in water, but the iodine is brown in water. Well, that equation is going to be bromine water being orange is going to react with colorless sodium iodide, and it's going to displace it, forming NaBr, which is colorless, and iodine, which is dark brown in water. Next. Write the ion equation for the displacement. Cancel the electrons. When you add these 2 equations together, the electrons are on opposite side. Just put them together. Everything on one side of the arrow. I always say draw a line on the arrow. So add that into one side and all of that on the other side, and you're done. Explain with reference to the appropriate species and electrons as to why this is a redox. Chlorine gains electrons, therefore reduction. Rig, oil rig, always super useful. Random question. Why does carbon take on so many forms like graphite and diamond? Yeah, these are called allotropes. Why does it? Because it has options. That is genuinely the answer. Because it can. Why does it? That's a really difficult question. Because it can. That's why. It can take on those forms. You're asking why does it? It's a really difficult question to answer that. It's because it can. That's all I can give. No. Oxidation is the loss of electrons. Reduction is the gain. So chlorine's gained in this case. And the astatine is lost. And it is both are happening at the same time. Yeah, remember that redox is the fact that there is reduction and oxidation occurring at the same time. Right, this is the decomposition. This is the thermal stability of carbonates. They've taken blue-green, it's nice for me to add colors to this, blue-green, copper, hang on a minute, I tell a lie. White, my apologies. They have taken white calcium carbonate, heated it, and they're bubbling the gas through lime water. Let's look at the equation. The calcium carbonate decomposes to give calcium oxide and CO2. The lime water will turn cloudy. What type of reaction is occurring? Thermal decomposition, the breaking down of a compound using heat. State the appearance of the lime water before and afterwards. It was clear at the beginning and turns white precipitate or milky or cloudy at the end. Describe how sulfur dioxide can change this, has caused this to change in appearance. The appearance of the marble has changed gradually over the years because of the effect of sulfur dioxide on the atmosphere. The SO2 reacts with the water to form sulfurous acid. Sulfurous acid is acidic and reacts with calcium carbonate in the marble. The calcium carbonate reacts with the sulfuric acid to make CO2, so it is eaten away, forming soluble calcium sulfate, which then washes away. Actually, tell a lie. Castro bear. Calcium sulfate is actually insoluble. Oh, no, that's calcium sulfite that is soluble. Ha! Sorry, I apologize. I'll stop talking. So anyway, you're going to eat the calcium carbonate away and you're going to form CO2. So it's going to form more bubbles on the surface and it will literally dissolve. Marble dissolves. There you go. Next, write a chemical equation for the decomposition of hydrogen peroxide. H2O2 goes to oxygen and water. And don't forget to balance, year 11. Describe the test to show that the gas syringe is oxygen. Place a glowing splint near the end and it will relight. Manganese 4 oxide is a catalyst. State and explain the effect on the catalyst. Right, that's really interesting. State and explain a catalyst on the rate. A catalyst increases the rate of a chemical reaction without being used up. There is state what a catalyst is. That is what is. Done. State what it is. Next, how does it work? State and explain the effect. So this is a catalyst provides an alternative route of reaction with a lower activation energy. Notice actually the bit I need to circle is the with a lower activation energy. More particles have EA, so there's more successful collisions. Right, graphs, rates. So the first one, we had a concentration has stayed this. What happened to the concentration? Concentration was halved for A, and the temperature stayed the same. So I'm going to make half as much. Remember, concentration is the particles per unit space. I have half the number of particles. I'm going to make exactly half the amount. So instead of making 60, I make 30 for A. And it's also going to go slower. Remember, how steep it is how fast it's going. So if you look at the steepness of those two, the A is less steep, so it's slower. The next one is the same concentration but higher temperature. Going to make exactly the same amount, but it will go up steeper, and it will end at the same height but earlier. So then sooner. Fast reaction. Heat for the blast. We did the blast furnace in metal extraction, which was nice. That was so carbon dioxide reacts with oxygen, forms CO2. Heat for the blast furnace. The next one produces the reducing agent and heat for the blast furnace. Right, calcium carbonate reacts as decomposed. So this is thermal decomposition, thermal decomp. And then this one is amazingly, sand is an acid and this is a base. That's a base and that's acidic. So they form then neutral calcium silicate. So that neutralizes it. Right, explain with reference to the reactants in the equation why this is a redox reaction. So this is now switched from doing electrons with oil rig to oxygen. So that one has lost oxygen whereas that one has gained them. So Fe2O3 loses oxygen, so reduction, and carbon gains, so oxidation. Both is happening at the same time, so redox. Next. Spot the anomaly. Oh, yeah, okay. Why does the mass decrease during heating? Because we're losing carbon dioxide to the atmosphere. The mass will therefore decrease. State the color of the solid before and after. There's the color I said you needed to know. Green, blue, blue, green, other way around, and copper oxide is black. In which experiment might the decomposition not have been complete? And that is number 1, because it has decreased, and it has not finished decreasing. Notice, that one has stopped decreasing, that one has stopped decreasing, and that one has stopped decreasing. Next, which statement could explain the decomposition may not be complete? Student didn't heat it to a high enough temperature. Seems very reasonable. Work out, attain the mass 3.4 grams. So they've just said they got 3.4, they were expecting 3.7. What they actually got versus the expected times 191.9%. Platinum will always have no reaction. That is the least reactive metal of all of them. So it'll never do anything in cold water, and it won't do anything in acid either. State the observation that is made with platinum, no change. Place the 4 metals in order of reactivity. That's easy enough. You just look at the bubbles. So we've got no change. So that the hard one is zinc, is the zinc and platinum for that and that. That's not very useful. But bubbles very slowly, bubbles very quickly. Most reactive, that's the most. Least reactive, of course, is going to be platinum. And then we have to say, right, where's the zinc? Oh, well, the platinum did no change with both, whereas the zinc had bubbles with the acids. So that one's going to be, and then the magnet. So we're going to have most. So number 1, most, second, third, and least. Next. Describe a test to show that the bubbles were hydrogen. Collect gas, light with a lit splint. Winkit. Will platinum react with fluorine? Yes. Yes, it will. Is there element fluorine will not react with? No. I'm pretty sure yes, there is. I tell a lie. Helium and neon. We've never reacted those two. Never done it. Yes, helium and neon. They're the only true. They are both at the moment. By the way, helium is the only real true noble gas. Helium will never react with anybody. It is the noblest of the nobles. Reactivity increasing down the group because they're, anyway, non-metals. No, it's actually my metal though, isn't it? That's awkward. Anyway, least reactive is helium won't ever react with anything, not even fluorine. And neon hasn't either yet. So yes. Next, word equation, fine. Suggest why the reaction between sodium and tire is not done. Too dangerous. That's easy enough. I said that to you earlier. Explosive. Next, they put zinc metal into copper sulfate. State what you would see. A pink solid forms on the zinc rod. That is copper metal. And the blue solution will not disappear. Wrong word. I've just lost that mark. Will turn colorless. Yeah. The reason being is the copper sulfate, that there is blue. And that reacts with the zinc to form colorless zinc sulfate and pink copper metal. And the blue color vanishes to go colorless solution. And the silver metal turns pink. Done. Next. Explain why it is not possible to determine the complete order of nickel zinc from these two experiments. They haven't done the third experiment. No experiment was performed between nickel and zinc salt solution. So we don't know which one's more reactive out of zinc or nickel. That one was actually quite a tough question, that. If you've got 3 metals, you can't just do 2 reactions. You've got to do 3. You've got to test the metals and their salts of the other person and see whether or not you see a displacement reaction happening. You need to do 3 experiments. Do more experiments. Explain why this is described as a redox. Zinc has lost electrons because it's become positive. Copper has gained electrons because it's gone from positive to neutral, and they both happened at the same time. Right, year 11. That brings us to the end of the periodic table. I'll do screen sharing. Stop. Hey guys, year 11, thanks so much for coming along to the webinar this evening. I hope it was useful. keep working hard. I know that you guys are working really tough now and you're putting in loads of effort for your GCSEs. I just want to say thank you for giving up your evening. I hope it was useful. Keep working hard. You guys are going to do great. I know you are. One last thing. Do you want to meet my dog? I got a dog. This is Lily. Look at Lily. Ah, I got an Ewok. It's not actually a dog. It's an Ewok. Mwah. Say hello, Lily. Say hello. Hello. Right, guys. Have a lovely rest of your evening, and I'll see you all tomorrow. See you, guys.